Hello students, I am going to briefly discuss about velocity triangles of Kaplan turbines and a few numerical problems related to that. As you all know, that Kaplan turbines are meant for high discharge and low head applications. These are basically axial flow machines. As you can see in figure 1 in the slide, here section 1 represents the outlet of the inlet guide vanes. Sections 2 and 3 represent the inlet and outlet sections of the moving blades which are mounted on the rotor. As you can see, this is a vertical axis turbine, and the flow after passing through the guide vanes takes a 90-degree turn and becomes axial. That is, the flow at the inlet and outlet of the rotor blade remains purely axial. When we say so, the distance of a streamline from the axis of the rotor shaft remains constant. That means the blade speed at the inlet of the rotor is equal to the blade speed at the outlet of the rotor. Now when we look at the cross-sectional view as shown in figure 1, we can see that the moving blades or the rotor blades connected to the rotor, when we view from the front, actually the cross-section looks like that of an airfoil. And in this figure, the rotor is rotating anti-clockwise when we view it from the top side. And if D0 and dB are the outer diameter and the boss diameter or the half diameter of the rotor, then the flow rate is equal to the axial velocity of flow multiplied by the area of the annulus, that is given by pi by 4 into D0 square minus dB square. For a fixed flow rate, it has to be seen that the axial velocity of flow remains constant in a Kaplan turbine. This is a very important point to remember. Now if we look at any particular cross section of the blade, as you can see, this is an aerofoil cross section of a Kaplan turbine blade, and here we want to discuss in figure 2 the inlet and outlet velocity triangles of a Kaplan turbine. So here is the inlet velocity triangle. Here alpha 2 is the inlet guide vane angle. That means it is the angle at which the absolute velocity approaches the blade with an angle of alpha 2 with reference to the blade speed given by u2. We all know that the relative velocity of flow is the vector difference of the absolute velocity v2 and the blade speed u2, and that's how we get the relative velocity at the inlet of the moving blade as vf2. The angle made by the relative velocity vector at blade inlet with the blade speed direction given by beta 2 is called the moving blade angle at inlet. Since the whirl component of velocity is very important in evaluating the performance of any turbine, here we can see that the whirl velocity at the inlet of the Kaplan turbine blade is expressed in terms of the axial velocity VA2 and the guide vane angle alpha 2, that is given by VW2 is equal to VA2 cot alpha 2. At the outlet, the flow lives purely in the axial direction. That means the axial velocity at outlet is equal to the absolute velocity of the flow at the outlet. That means the whirl component of velocity at the blade outlet given by VW3 has to be 0. The relative velocity at the blade outlet is again the vector difference of the absolute velocity at blade outlet and the blade velocity at the blade outlet, and that's how we get Vf3. For a smooth operation of a Kaplan turbine blade, the relative velocity at blade inlet should be tangential to the blade profile at blade inlet, and the relative velocity at blade outlet given by Vf3 should be tangential to the blade profile at the blade outlet. Accordingly, the angle made by the relative velocity vector with the blade velocity vector at outlet given by beta 3 is called the moving blade angle at the blade outlet. Now, with this knowledge, we are in a position to solve a few typical problems. So here is the first numerical problem. I am reading out the problem for you. A Kaplan turbine works under a head of 20 meter and develops 11,772 kilowatt of shaft power. The outer diameter of the impeller is d0 is equal to 3.5 meter and the boss diameter of the runner is db is equal to 1.75 meter. The guide blade angle at the extreme end of the runner is 35 degree. The hydraulic efficiency is eta h is equal to 88% and the overall efficiency eta naught is equal to 84%. Whirl velocity at the outlet is 0. That is, as we have just now discussed while discussing the velocity triangles, Vw3 is equal to 0. That means the absolute flow lives in the purely axial direction at the blade outlet. Now, determine the speed of the turbine. So we are going to find out the rotational speed of the turbine. So before moving onward with our solution, first let us note down all the given data. So PT is the power of the turbine, kilowatt converted into watt. H is the head, d0 is the outer diameter, dB is the inner diameter or the boss diameter, alpha 2 is the guide vane angle at the blade inlet, eta h hydraulic efficiency is 88% and eta naught the overall efficiency is 84%. So let the discharge be Q because it is not known to us at this moment. But then the available power to the turbine is rho GQH. This multiplied with the overall efficiency of the turbine will give us the power output of the turbine. That is PT is equal to eta naught into rho GQH. And when we solve this, we obtain the value of the discharge, which is 71.4 meter cube per second in this particular case. However, we also know that the discharge is also related to the axial velocity. And in this particular problem, the outer and inner diameter or the values of d0 and dB are known to us. The axial velocity is not known to us, but we can use the information about the discharge and the rotor diameters to find out the axial velocity, that is Q equal to pi by 4 d0 square minus dB square into VA, where VA is the axial velocity which has to remain constant at inlet and outlet of the rotor. So when we solve this, we find that the axial velocity is 9.89 meter per second. However, from the inlet velocity triangle, we know that the whirl velocity component at the blade inlet is Vw2 is equal to Va2 cot alpha 2. However, Va2 is equal to Va3 is equal to Va. And then we obtain the whirl velocity component at the inlet of the rotor as 14.12 meter per second. Please note that Vw3 is 0 as mentioned in the problem itself. Now the hydraulic efficiency of the Kaplan turbine is given by eta hydraulic is equal to Vw2U2 divided by GH. And when we simplify this, we obtain the blade velocity, that is 12.23 meter per second. Now the blade velocity at the extreme end of the runner is given by U2 equal to pi and d0 by 60, and when we simplify this, we obtain for the value of the rotational speed, that is 66.7 rpm. Now let us move to the second problem. A Kaplan turbine develops 9,000 kilowatt under a net head of 7.5 meter. Overall efficiency of the wheel is 86%. The speed ratio based on outer diameter is 2.2 and the flow ratio is 0.66. Diameter of the boss is 0.35 times the external diameter of the wheel. Determine the diameter of the runner and the specific speed of the runner. So in this case, we have to find out d naught and ns. In order to find ns, that is the specific speed, we have to first find the rotational speed n of the turbine. Now here is the available data, and please note here that Ku naught equal to 2.2 is the speed ratio, Kf equal to 0.66 is the flow ratio. We shall shortly come to know what are these parameters about. The speed ratio based on the outer diameter is given by Ku naught is equal to U naught divided by square root of twice GH, where U naught is the blade speed at the outer diameter of the runner. When we simplify this with the given information, we find out the blade velocity at the outer diameter of the runner. Also, if the discharge is Q, then we all know that the power output is related to the overall efficiency, discharge and head by Pt equal to eta naught into rho GQH. And when we simplify this, we obtain the discharge as 142.23 meter cube per second. However, if Va is the axial velocity through the Kaplan turbine, then the flow coefficient is given by Kf equal to Va by square root of 2gh, and when we simplify this with the known data, we can find out the axial velocity through the turbine. Further, the axial velocity is related to the blade dimensions and the discharge by this expression, that is Q equal to pi by 4 d naught square minus dB square into Va. Since d naught and dB is given as a particular ratio, that is dB by d naught is given by 0.35, hence we can express this equation as Q equal to pi by 4 d naught square whole into 1 minus 0.35 square whole into Va. And when we simplify this, we obtain for the value of the square of the outer diameter, and when we take the square root of this, we find out the blade dimension, that is the outer diameter of the rotor is equal to 5.08 meter. Once we know the outer diameter, we can find out the relation between the rotational speed, the outer diameter, and the blade speed at the outer periphery of the rotor. And when we simplify this, we obtain the rotational speed of the turbine as 100.27 rpm. Now, the specific speed of a turbine runner is given by ns equal to n root pt divided by h to the power 5 by 4. Please note that pt has to be in kilowatt, and h has to be in meter, and n has to be in rpm. And when we simplify this, we obtain the specific speed of the turbine as 766.42. The students, thank you.